Yeah, great.
So the program of today is not cooperating. We have a presentation of the results from the project Electric Light, trends within battery technology, battery safety. Then we will have a short coffee break. And after that, we will hear the perspective of a port. What about the grid? And last but not least, the project Sea Lion about energy storage systems in the ports of Gothenburg and Kiel. And then hopefully there will be some time for questions and discussion, and we will end no later than 11. And before we start, I would just like to show this. I think most of you know what Lighthouse is, but I would say it anyway. We're a Swedish collaboration platform for maritime research and innovation, and our vision is sustainable shipping. And if you want to know more, you can look at our website. So our first presentation is about the results from this project. And this presentation will be given by Mikael Hägg, who is responsible for the maritime research at RISE, and Bengt Ramne, professor of the practice at Chalmers and also CEO of Scandinavian. Welcome, Mikael and Bengt.
Yes, good morning, everyone. And I'm very, very glad to try to give you some results from our innovation project that is called Lätta elfartyg. And this project has been conducted by RISE and Chalmers and in a very, very close cooperation with our industrial partners, ABB, Stena, and Wallenius. And the project is funded by the Swedish Transport Administration's industry program, Sustainable Shipping. Next slide, please. So, Lätta elfartyg in Swedish, that implies two things, lightweight and also electric propulsion. And for this project, we have used RoPax as a type of vessel, as a scenario for this design. And we have also looked at the fully electric vessel and tried to really see what that means. How would that affect the overall concept? So the objective of the project have been to look at this an innovative concept for electric powered RoPax vessel or ship. We have looked at the propulsion and the electrical design. We have also tried to answer the question, how much lighter can this type of ship be? I mean, we will remove some main engines and also bunker, and instead we will have a lot of batteries. We have also done optimized the design for weight, speed, and range for a certain use case or scenario. And the concept includes a lot of new technical solutions. We have also looked at risks for especially connected to the electrical systems. Next slide, please. So here you can see the use case, the scenario that we have worked with. It's a route between Gothenburg and Fredrikshavn. And we have used 2 trips per day. And that means roughly that you have 1.5 hours in port. And we have used, say, roughly 1 hour for charging the batteries. So that puts some constraints on the design. And then you can see the route here, and we have a speed profile with a low speed in the fairway and also to the port entrance, and a bit higher speed at the open sea. And it's this speed that we have tried to optimize with respect to storage and also charging capacity. So we ended up with 17-18 knots. We have also used this area for design rules. So we have looked at the wave characteristics, etc., and used DNV design rules service area restriction R3 for the design. And then I hand over to Bengt for the continuing with the design.
Yes, good morning. This is then the result of this project. The general arrangement, maybe a bit too detailed to go through the screen to you, but trust me, it's a carefully drafted general arrangement. It's based, let's say, our reference vessels were Stena Trader and Stena Exporter, which are then two well-performing, let's say, typical well-performing Ropax vessels from the Stena fleet. So this vessel has 3 decks. It's a little bit differently arranged compared to the conventional. We will get back into that a little bit. But the biggest difference from the reference is it's shorter. This one is 178 meters compared to reference vessels of 210. So we have reduced the length by about 15% by utilizing the possibilities that the fully electric propulsion system provides. The beam is kept the same. The deck to the entry height to the entry deck is similar, and also the draft. And we have reached 3,000 meters plus, and the 1,000 passengers. In the concept here, we ended up with a propulsion system with 3 times 4 megawatt acipods. Acipods, it's a good, let's say, it's for a diesel powered ship, there could be question about the huge benefit of acipod, but for a fully electric ship, the acipod really provides a possibility to utilize the fully electric concept to very good result. And difference from the reference is that we have a lower design speed. In general, energy on board and a full electric ship is much more precious. We cannot waste it. We need to really take care of it, and that means that we will lower the design speed and operation. Well, we lower the operational speed, and there is no really reason to have a lot of margins for the design speed. So compared to the reference is 22, we have 19 knots, and then we have a battery storage capacity of 60 something megawatt hours. We could actually fit another 20 in the arrangement we have now, but the 60 is for the design for the operation. Next slide, please. So this is a 3D view of what we have done. All electric, 3,000 meters, 1,000 passengers. The battery capacity of 60 megawatt hours, it's 10 times more than any today designed electric vessel. So it means that we really make a leap in the design process when we going for this type of vessel. It's still, we think it's reasonable. It will be about 600 tons, which is a lot of weight, but not a huge amount of weight. It's a little bit similar to what you would have for bunkering in a conventional vessel. And it's designed then for regular service of 50 nautical miles from Gothenburg to Frederikshavn, for example, in 3 hours and 45 minutes. And there is a good thing with the batteries is that you like to design it so you're not utilizing the full range of the battery loading range. We typically would use 50%. In order to have long lifetime of the batteries. And that also gives us, by that concept, also gives us a good redundancy that we can have sufficient power for return to port. So that's a good thing with this. Weight optimization, there is no so much to gain from exotic material. Not at least if you are considered cost benefit, but we do gain a lot of weight by reducing the size, the length of the ship, and also as Mikael mentioned before, we are not designing this for a worldwide operation. It's designed for for respective service area R3. So what we do here is that it's not designed to go anywhere on the, it's designed for this particular route in order to reduce the scantlings. And the other thing here when it comes to electricity is that we're now pushing the boundaries for a DC grid capacity. On the what you see on this on the slide here, it's actually we have 2 times 6 megawatts on this particular example. That was more than we could feed with a DC system. So that's where we then eventually went with 3 times 4 megawatts, because that was today considered to be the limit for how much we could get out of the DC system. Next slide, please. So then you only get that far with your naval architectural skills in order to make things appealing. We brought in some support, some design support, which turned our concept into this very nice view. I think it represents the concept very well. It's contemporary. It's not futuristic, and with that, the message is that this can be achieved with existing technology. It has to be refined. It has to be further developed, but there is no breakthrough development needed. So the concept it will. The technology is there to make this concept feasible. So that's the message. I think we take the next slide and I leave it back to Mika.
So we'll say some words about the propulsion, and as Bengt mentioned, we have used as a pod, and one of the reasons was, as mentioned, to save some volume, some space that can be used for cargo instead. And for this design speed, the rated propulsion power is 12 megawatt. So we have used 3 ASSI pods, and you can see a typical ASSI pod. You can see here is ABB's, a version of ABB's ASSI pod. And these ASSI pods has been fed by a DC grid system. I will show that a bit later. So next slide, please. So with this design speed and with the possibility of 1 hour charging, battery charging, we have used a storage of 60 megawatt hours. And as Bengt said, we have used the batteries, tried to use the batteries optimized with the depth of discharge of 50%. And this is also due to safety, to have some safety margins. Also, it's very important to have redundancy. I mean, the concept need to handle several different types of failure and still be able to take the vessel into a port at least some speed. So therefore, we have looked at electrical system and divided that into switchboard, and each switchboard has been connected to a multiple battery strings. And we have a flexibility between the switchboards and the batteries. Next slide, please. So here you can see an overview of the electrical system. On the right-hand side, you see an AC configuration for the power transmission. And on the left-hand side, you can see a DC configuration. And we have selected, for this concept, we have selected the DC configuration. And the reason for that is a higher efficiency and also lesser overall weight of the system. I don't know, Bengt, do you want to add something for the electrical design?
No, I think that's the most relevant part.
Okay, then we can take the next slide. We have a lot of new technical solutions here in this concept, and it's important to follow that with risk analysis in parallel all the way. And we start to look at the different national regulations on electrical vessels, also the guidelines from class societies. And we also performed hazard and also risk analysis. And based on all that input, we come up with a draft battery fire safety concept. And this is actually a quite generic concept for a fully electrical powered ship. And we will discuss this concept a bit later in more details at the later presentations. So I leave that to Ola. And we can continue to next slide. One of the critical issues was the location of batteries. In the first design, we put the batteries very low in the vessel, in the double bottom. At the same time, that there might be a risk of intrusion of salt water, maybe when with the grounding or at the collision or something like that. So we moved up the batteries, and we have also looked at this design, and the conclusion in the project is that it's manageable to have an intrusion of salt water with the normal ventilation. And Ola will explain this in more detail in a later presentation. So next slide, please. Then hand over to Bengt again.
Yes, so coming to the conclusions, we conclude from this work we have done that we can reach close to 100% CO2 reduction. Of course, you have to consider life cycle, analyze all the material, but we are getting quite close. We actually can gain some benefits with not having the combustion engines. We can reduce the size of the vessel by 50%, or we can increase the cargo capacity with the same size with 50%. The weight will be quite similar to a conventional vessel. There will not be a huge difference. It will be more expensive, approximate 20%, we estimate. 30% of the total ship cost is the batteries. But compared to a conventional ship, we can eliminate the number of systems, which reduces that cost with 10%. So the result is that the total cost for all electric ship would be 20% more expensive. We have lowered the design speed. And the most significant thing is that we have limited endurance range. We have 50 nautical miles, which compared to conventional ship of maybe typical 10,000 nautical miles. So we have reduced the range with 200 times, which means that this ship cannot on its own power go from the shipyard to the operation area or change operation area, but that's how it has to be. Very significant, we lower the fuel energy cost 16 to 72%, depending on what we are comparing to. I will show you a slide later on this. And more important, the total cost of operation for an all-electric ship is between 80 and 150% of a conventional vessel. So it means that depending how we do the comparison, we are in the range of a conventional vessel. Next slide, please. So this slide is the other conclusion from significant or most relevant conclusion from the project. We have earlier shown that the technical part, we see that it's feasible, it's possible with existing technology to design and build this ship. And this is the slide that shows why it will happen. So if you sort of focus a bit, I will explain it to you. The purple line in the graph that starts at the left at 18 euro per megawatt hour is the total cost for energy delivered to the propeller for a marine gas operated ship, a conventional ship. And there we have included the cost for the vessel, capital cost of the vessel, the operation cost, and the fuel cost. And since marine gas on, as you know, it shifts over time, the total cost shifts as well. But this is how, if we backtrack a couple of years, see how that has moved. The dashed dotted red line above is the cost, how it would have been for an electric ship based on the investment cost and the electrical cost. If we assume that the batteries will have a lifetime of 10 years, which means that we will have to replace the batteries. And then we see it will be a little bit more expensive than a conventional. But if the batteries will have a lifetime of 20 years, we can see that the electric ship would actually have outperformed the conventional vessel when it comes to the total cost. So this is, I think, a clear picture why this is going to happen. And then maybe the more important thing is that when we now go for electricity, we actually removing, or we going from fossil fuel. we will then reduce the CO2 from emissions from the ship. And the other way to remove CO2 emissions from the ship would be to go with liquid fossil renewable fuel like HVO or methanol. And we don't have detailed data for that, but it can be assumed that the cost for renewable liquid fuel would be about twice the cost as fossil fuel. So if we then see that we can achieve going all electric for this kind is the by far most cost-efficient way to reduce the CO2 emission. It's about half the price to the alternative if you would go with liquid fuel. So I think this is, to me, a very clear, let's say, proof that this ship we'll see the realization of this ship, and I think it will be a trendsetter for a lot of other operators. With that, I say thank you very much.
That concludes our presentation.
Thank you. Thank you very much. And are there any quick questions from the audience? I will give one when they're thinking. Are there any specific findings in this project that surprised you, or did it come out the way you thought?
I was surprised at how feasible it was. I came from the opinion that electricity is very difficult for this kind, but that it should be very difficult to scale up things to this level. But I think from technical point of view, I'd see that it's actually the technology is there. And I think that we didn't talk about that, but really the biggest issue here, the remaining bottleneck, is the charging infrastructure.
We will come to that later.
That's the interface. I think that's the remaining big issue to solve.
Will it be easier or harder to build and operate such a ship like this? Will it be the same, done with conventional methods and so on?
I think it will be easier. I think we can guess that the maintenance for the electric propulsion line will be less than for conventional combustion. That will for sure require different skills, and we maybe haven't seen completely the consequences of these large battery installations, but the qualified guess would be that it should be cheaper and require less maintenance.
Okay, thank you. And Arash has a question, so welcome.
Yes, thank you very much. Thank you, Mikael. Thank you, Bengt. Just a quick question about what happens after the service time, after the life cycle of the ship. What about the cost of scrapping the ship? Is it going to be similar to conventional ones, or what happens to the batteries? Do you have any progress on that?
I can start just to say that we have not included the life cycle in the project. We focused on the sort of the operational life, but it's, of course, it's a very relevant question. Maybe we come into that later on with the battery technology, or do you have any answer, Bengt?
No, I don't. I think it depends, as you said, on the battery, but I can see that the residual value of an old battery is probably higher than, so there will be more things on an all-electric ship that could be recycled and have a second life than on a conventional vessel.
Christer?
Hello, Christer Bruselius is my name. I represent the Gotland Tech Development and we are operating Ropax vessels between Gotland and the mainland. And you mentioned, if I understood it right, you mentioned that you had only used half of the possible capacity of the battery installation. You could actually double the battery installation. Did I get that right?
I guess the concept is that we have 60 megawatt hours installed battery. One single trip required 30 megawatt hours. So, but that for two reasons. One is that we normally work between 90 and 40% depth of discharge, because that's a good range for the battery and extends the lifetime of the battery. But it does also mean that we do have, for emergency situation, once in a while, we can certainly utilize the full battery capacity. But when it comes to how you size the battery package, this is the, let's say, the typical way to do it today, that you have installed twice as much that you normally would use.
But could you install, I got the feeling that you could install 120 if you were using all the space that you have in the ship. Did I get that right?
That would be about, we would have another 20 megawatts. So yeah, about 80 megawatt hours would fit into the space that we have available. But of course, we can, if needed, we certainly can arrange it differently or so, but with the design we have, we could extend.
So you could foresee a speed up to, you have 18 knots, you could maybe come up to something like 22 as a service speed?
Yeah, I don't see that's really possible, because I think that would even push our requirements for the charging infrastructure. So I think before we consider that, we would solve the problem with how to recharge the vessel.
Okay. Thanks very much.
Thank you. Now we need to go to the next speaker. Thank you very much, Bengt and Mikael and Christian Arish, for your questions. And our next speaker is Thomas Tegnér from ABB, who's responsible globally for energy storage. And we're fortunate to have you today participating, since you're very busy moving, but you could squeeze this into your schedule. And thank you for that.
Yes, that's right. Thank you for the introduction. Yes, I am a global product manager for energy storage within ABB Marine and Ports. So Marine, ABB, I mean, is of course a big company with a lot of different business units, and I'm in the ABB Marine and Ports, based in Norway. Pardon?
That's the part that matters to us. So.
Yeah, exactly. So can I flip the slides, or will you do that for me?
I will do that, so you just say next, and I will stop.
Okay, good. So just a very quick overview about ABB Marine and Ports. We are a unit, as I said, in ABB with a global footprint. We're approximately 2,000 employees. We are arranged in 6 different hubs around the world, and then we have service centers in many more countries. We work with propulsion solutions as the Assipod that was mentioned previously, the electric solutions with which energy storage is one part of, and then the digital solutions and services. Next slide, please. Here is an overview a little bit of what we are doing. We are active in most vessel segments, from large cruise vessels to offshore, to passenger vessels, and also the passenger vessels we go to actually also quite small ferries. For the core solutions, I will not talk much about that, more than that we will speak about the battery solutions today. So next slide, please. When it comes to energy storage, or specifically electrical energy storage, there are many different ways to store electricity, and what is happening now is that batteries, and especially the lithium-ion battery, is taking over completely, you could say. It is very challenging for many good startups to compete with the lithium-ion battery. So many technologies that were in development, maybe half a decade ago and so, they have basically no future now, because the tremendous development of lithium-ion. So next slide, please. Okay, you need to click through these pictures. Sorry for that. In ABB Marine, we have a few different technologies for zero emission technology, so to say. We have charging solutions, which is one very important topic when considering electrification of vessels. We have the onboard DC grid that connects everything on the vessel. We have the batteries, and we have also fuel cell solutions. Next slide, please. When we look into batteries, the different technologies, we have the well-known lead-acid battery, what you still have in your car as a starter battery. In the 90s, we got the nickel metal hydride battery that was also used in the first OEM electric cars, but that was quite quickly also replaced by lithium-ion batteries. And you see here how wide range that the lithium-ion battery covers in terms of energy density and power density compared to the other technologies. And not only the power and the energy density is extraordinary for lithium-ion batteries, but also the lifetime and cycle life. And now with the large scale up of production mainly for the automotive, also the cost comes down significantly. So this is a very exciting development. Next slide, please. As I pointed out, the lithium-ion battery has performance advantages. It is flexible in terms of formats and shapes, how you arrange it, but also in terms of optimization for either cycle life or power density or energy density, or a combination of those. And we see the cost continue to go down. Unfortunately, we haven't seen that materialize so much in the marine industry yet, mainly because marine is a very small market for lithium-ion batteries. It's a small market and with specific requirements about safety. So it's not straightforward to utilize products that are developed for other markets. Therefore, we are quite a bit more expensive than, for example, batteries for automotive. But hopefully that gap will close gradually. Next slide, please. When talking about lithium-ion batteries, that is not only one chemistry, so to say. It is actually a family of materials. On the cathode side, so you can see the cathode as let's say a container or a reservoir of lithium ions at the high potential, and then the cathode is the reservoir on the low potential. And if you make the analogy to water or hydro storage, the voltage potential would be the height of a reservoir, while the storage capacity is the size of the reservoir. So naturally, I mean, what we want to have is high capacity and high potential. Then we can store as much energy as possible. And for that, graphite is typically used on the anode side, which has a very, let's say, a lower potential, so it gives the total cell voltage that is high. But the challenge with this is that we have you can see on the picture to the right, a solid electrolyte interface that is needed to stabilize the electrolyte, and that introduces resistance, especially during the charging phase. So fast charging becomes more challenging. Also, the potential margin down to lithium metal is small. So if you charge a battery with graphite anode fast, you may plate lithium on the surface and damage the battery. And for that reason, lithium titanate oxide is also used for technologies that require very high cycle life and fast charge rates. And then these can be combined with either of these cathode materials. The trend is to reduce the amount of cobalt in all these materials. Lithium iron phosphate is starting to gain more interest now, and the Corvus blue whale battery that was mentioned is actually lithium iron phosphate chemistry. But also the NMC and NCA materials are being optimized now for less cobalt, higher nickel. That increases the energy density, and it gets rid of the problematic cobalt. Okay, next slide, please. This slide, I will not spend too much time. It's just like a indication that these lithium-ion chemistries that are boxed in a red square basically have their clear advantages versus other technologies. But we can skip to the next slide. When we see, I mentioned the scale up, and that is what is quite exciting. So the annual production of lithium-ion batteries is increasing tremendously, and with lithium-ion batteries, it is really a matter of scale. You have huge economy of scale benefits when scaling up. As you can see here, the automotive industry is dominating completely. We also have a relatively big market for consumer applications. Can be like e-scooters and laptops, mobiles, and so on. And then we have heavy duty applications, the black one there, and there I would categorize also the marine segment as a subsection of this heavy duty. And then we have the stationary storage. So the marine segment here is just a tiny slice of the black line. So that is the true challenge for our industry, to be able to tap into the economy of scale from these larger industries, while at the same time having specific requirements that are not present in the marine in the mass market industries. Thank you. So here is an illustration showing the previous technologies or the mature technologies, and then the introduction of lithium ion. And basically the trend now is really to reduce the cobalt content, increase nickel content to get energy density up. On the anode side, mixing the graphite with silicon to boost the capacity on the anode side. Then we see, I mean, this more far-fetched next generation technologies like all solid state batteries, lithium air or metal air batteries, and also lithium sulfur, which I would say they are at the horizon, but it is still far away. And the question is really, will they be able to compete with the conventional lithium-ion battery that is just dropping in cost all the time? It's so for the we can go to next slide, by the way. So here I pointed out a few of those trends. So NMC 811 is like the new standard on the cathode side. Silicon, and then there is some development in different cell formats to reduce the packs cost. For fast charging batteries, and here I could also mention some lithium ion capacitor development that is going on that start to a little bit nag into the edge of these high power, high cycle life lithium-ion batteries. We have the solid state batteries, as I mentioned. Question is, can they be industrialized in scale to meet the cost parity or even exceed the cost of lithium-ion? Yeah, we have this trend of reducing cobalt or get rid of it completely. Lithium iron phosphate, which is already quite mature. Lithium ion technology do not have any cobalt at all, so there are already technologies available for that. Yeah, we have some development also for sodium ion batteries that might have an advantage for some applications. Sodium is a lot more available than lithium. So that could be one reason to explore sodium ions. And then we have this, yeah, beyond the lithium batteries. So lithium sulfur, lithium air, aluminum air batteries. These are all very far away in what we believe in ABB at least. Next slide. So quickly about the solid state battery, because we get a lot of questions about the solid state battery from potential customers and from other industry stakeholders, and this shows the concept. It's quite clear that if we can replace the hosting material on the anode side with pure lithium metal, we can increase the energy density significantly, because then we will not have any, let's say, dead material on the anode side. The anode would itself be the active material. So that can improve the volumetric and gravimetric energy density quite significantly, but there are a lot of challenges to be solved. And it's really, yeah, it is technical challenges. And then beside that also the challenge of production at scale. Now the gigafactories that are being built, they are built for producing conventional lithium-ion batteries, and they will do so at a very low cost. So that, I think, will be the biggest challenge for any new battery technology. Yeah, I can also mention that this solid state battery have a potential to improve the safety characteristics of the battery. A conventional battery has a organic liquid electrolyte, and in case of a thermal runaway, this electrolyte will be highly combustible and potentially cause explosive atmospheres as well in the battery compartment. With solid electrolyte, you don't have that contribution from the electrolyte in a thermal runaway incident, which will most likely improve the safety characteristics of the system. Yeah, we think that solid state batteries will not become relevant for our industry within 5 to 10 years. It will most likely take at least 10 years before it becomes relevant. But you never know, of course, because it is also massive amount of research and effort going into battery development now. So some people in the industry compare now the development in battery technology as the development with microprocessors in the early 2000s. If you remember when we had the Pentium, and then we got the Pentium 2 and the Pentium 3 and the Pentium 4, and you know, technology was irrelevant after just a few years. It is a little bit like this now, and that is also a challenge when we are looking into our projects that typically have quite long lead times, and it do not really make sense to define what battery to use if the installation will happen in 5 years, because it will be a better technology available then. So starting a project, starting the concept without, you know, sticking too much to a specific battery solution, that might be a challenge. But just to summarize, the massive production increase of lithium-ion batteries drives the cost down, and it increases the performance as well. Lithium-ion will continue to dominate the market for a decade at least. Higher energy density by increased nickel content in the cathode, and silicon composite, graphite composite on the anode side. That is the main trend. And the all solid state battery is very interesting, has potentially characteristics that would be very nice in the marine battery market, but it's still far away. So that concludes my presentation. Thank you.
Thank you very much, Thomas. Very interesting. And I will just ask a question on the last, all solid state battery as the holy grail. Do you think these are necessary to make longer sea journeys possible?
That depends on what we mean with longer, of course. The solid state battery can increase energy density by effect, maybe by 50 to 100% in the best case. So that would, in the case of this Lätta elfartyg project, enable routes maybe up to 100 nautical miles or something like this. But we still need to solve the charging. So we need to get the power into the vessel at some point. So that is the second challenge, and we will get to that in a later presentation.
Per Wimby from Stena wants to ask a question, please.
Thank you, Thomas. Very nice presentation. I just had a question about the price. What is your trend there in cost of batteries? Any news?
Yeah, I can say like this. We see that the general trend now from existing marine battery suppliers is quite moderate cost reduction of 3 to 5% per year, something in that range. But that is with existing technology. With cells that were selected a few years ago. And with new product development, I do expect that we will see stepwise cost reduction.
Are there any other questions? You can also post them in the end. Are you with us all the time, Thomas, or do you have to carry boxes?
I should carry boxes, but it is interesting topics. I will try to prioritize to stay.
Okay, thank you very much. And this is your last slide, so everybody knows that you come from ABB, Marine and Ports. That is what the important part of ABB. Our next speaker is Ola Windstrand, and he comes from RISE, and he will talk about the topic of battery safety, which will now be addressed more thoroughly. And Ola has worked at RISE since 2013. He's a project manager and researcher who's really focusing on battery fire safety, and has also started a PhD in battery fires. And before Ola starts, I would like to say that there are many interesting questions, and I do hope that you will stay, even though we might not be able to finish at 11. Because I want to give all the speakers a chance to actually go through their presentations. So I hope it's okay.
Yeah, thank you. So battery fire safety, we can go to next slide directly, since you introduced me. So just a short video of what a battery fire is. Maybe I've seen. So you can start the video. So this is just a battery module where you have thermal runaway, and this video quite clearly shows also that it's quite hard to extinguish. You see very soon that even if you do extinguish the flames, you could see that you still produce a lot of flammable gas, as you see here. and which could at any time reignite. So I mean, to stop, you really have to cool this, and this is just to show what a battery fire is, and this, of course, we don't want. So that's why it's important with battery fire safety, and that's what I'm going to talk about. So next slide. And yes, as Mikael mentioned, the Electric Light project, we did some actions and drafted a battery fire safety concept that should be quite general and generic. We can go to the next slide directly. And we focused on fire safety. That's the most important for me with regard to safety, of course. For a holistic perspective in rules and regulations and so on, you should also have parts covering the electrical safety and battery design and so on. So this is focusing on fire safety. I think it could be a good starting point for discussion of harmonized rules together with classification societies and so on. And what is seen here is just the parts that we covered and discussed and formulated some basic requirements and concepts around, and we can take the next slide to go through those a little more detail. So coming to thermal runaway integrity, we don't require, but says that it should be, of course, strive to achieve this at already at cell level for high safety. And of course, it should be verified by tests. In this project, we defined something that we call the casualty unit, since we thought we need some battery unit or minimum or safety level that we also design our ventilation for, or explosion integrity. And yeah, you can click once more. And this is, of course, connected to if you click once more. Yeah, so the casualty unit. So this is, of course, connected to the thermal runaway propagation protection we should test. But we also think that, okay, even if you achieve this at cell level, maybe you should still design your safety not only based on this, because I mean, working at a testing institute and doing battery tests, we know that it's not always that the outcome is what the product supplier believe, so to say. So I think it's this could, of course, be defined in different ways, but as we did, we said that, okay, you should have thermal runaway propagation. You should look at which level you have the external short circuit protection. Could be on cell level, could be on module level, but also we think it's important if the cells are parallel or series connected. So if you have a unit of parallel connected cells, and even in the case you have tested your thermal runaway propagation, which is normally just done by heating one cell, and you also have external short circuit on cell level, we could see that if you have a cell failure, for example, then you will short also the parallel connected cells, which, of course, if those are protected, will not cause thermal runaway maybe, but it will still give some heat buildup in those cells. And then in combination with the thermal runaway in the initiating cells, it could in some cases propagate. So yeah, enough talk about that, but I think it's very important to define some unit or safety level that you design your systems around. Next slide, please. And yeah, what's the risk of thermal runaway? I could give you a separate presentation on this one, and I will not talk a lot about this. I mean, you could talk about the causes and statistics and the probability and so on. I will just mention that you have, of course, your safety systems, which is very important. The battery management systems, you can have passive protection in the cells and so on. But basically, you can protect against a lot, but you cannot protect if you have an internal shortage in one cell, for example. It could be due to manufacturing flaws or in combination with aging effects and so on. You also have the mechanical damage, risk of mechanical damage may be higher if you have a car in a ship. Of course, you should not place your battery space in the collision zone, but you also have shock forces in a collision. And then you have the last one here, also external heating high, which is typically external fire, which is also hard to protect against. It could also be that you have your battery in a container on weather deck and very hot climate, but then in that case, you should also design your thermal management system and cooling system to be able to handle that temperature variations. Next slide, please. So the structural integrity, I will not talk too much about this, but we put some requirements on location and especially on compartmentalization for redundancy. Regarding fire integrity, it should be at least the same as for machinery spaces, and as I also mentioned, the explosion integrity should be connected and to the amount of gases that could be produced from this defined casualty unit. Also in combination with your ventilation system, what flammable gas cloud you could produce, for example. Next slide. So regarding ventilation, here we also define some new concepts or new levels. So we said, okay, basic ventilation in the battery space is typically what you have in such a space, 6 air changes per hour, for example. In case the battery is not enclosed with separate ventilation, which it could also be open racks, then you should also at least achieve the preventive ventilation that should be able to ventilate the gases produced from one single cell. So this should of course be tested how much gas that is. It could be different for different cells. And then you also have the casualty ventilation, which you should activate in case of detection or in case of thermal runaway, that then should be able to ventilate the gases produced from one casualty unit. Next slide. Regarding detection, smoke detection should be the basis. You should also have some kind of early indication of thermal runaway. CO could be good one, gas detection, and such early detection should then disconnect the module or string and also activate the casualty ventilation. And also feedback is important, since we know that battery fires could be difficult and it could reignite, and you really need to know what is happening within the battery space if something happens. Next one. Regarding fire suppression, we chose to define 2 different types of system that could be, we call them total compartment fire suppression and initial response fire suppression. This could be fulfilled with one system. So depending on the system you chose, both those could be fulfilled with one system, or if you have 2 systems. But just to see what we mean here is that for the total compartment fire suppression, the main performance objective is to suppress fires that is not in the batteries, and to prevent fire spread to the batteries, and also prevent fire spread to and from the space. So this is basically what you have in a machinery space as a starting point. And then then you should also have the initial response fire suppression that could more swiftly suppress a small fire without damaging the battery, and it could also assist in prevention. If you have your casualty unit involved in a fire, then this suppression system should also assist in prevention, prevent further propagation. And here you could have for example, a gas system or a freshwater system as a starting point. Next slide. And then testing is very important, of course, and all battery systems behave different, so all systems should be tested. You should have a prevention test, of course, that thermal runaway is not started. Thermal runaway propagation test, and also measurement of the gas released from one cell and from the casualty unit to be able to define your or design your ventilation system. EP classification tests, of course, is important if you have water suppression media, for example. Next one. Yeah, impact of salt water. This was discussed a lot in the project, as Mikael mentioned. Yeah, I mean, it could be as concluded. I mean, we did some calculations, also some small tests with regard to the production of hydrogen due to electrolysis. I mean, if you put a battery in salt water, you have hydrogen production. We also looked at short circuit risk. Typically, you would need at least 100-200 volts for a short circuit in salt water, and in our case, we said, okay, we have fuses protecting against the short circuits on that level, and cells should not short due to salt water. You can see in the next slide also just pictures from the tests we did with focus on the production rate of hydrogen. Yeah, we didn't have any short here for cells, but as you see in the pictures to the right, you also have a lot of corrosion due to the salt water you see in the water, for example. And of course, I mean, we did this test in 4 hours, but this could be studied further. I think, okay, what will be the effect, the long-term effects, and also if you have submerging salt water, and what about when they're not submerged anymore, and the risks in that state and so on. But on a short time, we think it should not be that high risk. Next slide. And yeah, summing up, we also just identified, I mean, future work needs in the project, and as I just mentioned, there should be more testing of battery immersion into salt water. The ventilation concept is very important, and the design risk level, that's the casualty unit, as I talked about, post-fire strategies, early detection, testing requirements for marine applications. Okay, should this be the same? I mean, test standards is a bit lagging behind standards generally, and okay, should we just use what is used on land and so on? IMO harmonized rules is not in place, and yeah, also here, what we also already have a project proposal on is to study further the ventilation concept and the post-fire strategies. So that's my last slide. Yeah, just further details about what should be studied in this new project that we hopefully get approved. Yeah, so that's all for me, I think. Thank you.
Thank you very much, Ola. And if anybody is really interested in participating in this new project that you are proposing, they should, of course, contact you. Isn't that right?
Correct.
Okay, do we have any questions to you from the audience? I could ask you, what do you foresee regarding development of regulations and guidelines? Will they be quick enough, or will they?
Yeah, I mean, for now, the classification societies have the best regulations so far, and of course those are continuously developed, and I also know that EMSA has initiated some work on this, and hopefully we will be involved in that work, and I think it's important, but it's, of course, it's maybe a bit lagging behind. But
is it possible for you and Sweden to participate?
Yeah. I mean, we want to participate, and hopefully we will be. I mean, we have had discussion with the transport agency and so on. So we will probably be involved in the work.
Thomas has a question.
Yes, I do. Thank you for an interesting presentation, Ola. I have a question about the salt water, and you mentioned there that we have fuses that would protect from hydrogen production. Was that how I understood? Did I understand that correctly?
No. That was, I mean, the electrolysis and the hydrogen production is one thing, and that's our conclusion. There was, even if we submerge the complete battery space, we don't get more hydrogen than could be handled by the normal ventilation system. With regard to short circuits and the risk of thermal runaway due to short circuit, that should only occur on so to say high voltage level where you have fuses. We should protect.
But yeah, okay. But I was thinking, because if you have, I mean, battery modules doesn't necessarily have fuses built in. There are many marine battery systems without internal fuses.
Yeah, that's true. But in this design case, we had fuses on module levels. That was our conclusion in this project.
Okay. Okay, so that was the base assumption, basically.
Yeah, exactly.
Okay, then I understand. Because when we do not have that, of course, then we can get high voltage shorts caused by the salt water, and that would possibly also generate a lot of hydrogen and the explosives. So that was just a comment.
Yeah, you're right. And hydrogen is produced when you get the thermal runaway. Yes.
Yeah.
Wimby also has a question.
Yes, I had the question regarding regulations. Since this is happening so quick now, is there a risk that the regulators will be conservative rules? For example, now in DNV rules that you're only allowed to have batteries, they should be positioned in a separate room. We are not allowed to have any other things in that room. What's your view on that?
Yeah, I mean, hopefully we will end up on a suitable level. Of course, some will always think it's too conservative, and some will not. But what should I say? I mean, I don't know at this stage what it will end at, so to say. But
Okay, we'll have to come back to that then, maybe in a later webinar. Are there any other questions? Well, thank you very much, Ola. And we will now have a short coffee break, and stretch your legs and things like that. And please be back at 10:15, and then we will continue. So, thank you. Hello and welcome back. Hope you have gotten your coffee and stretched your legs. And now to something completely different, but maybe not so different. It has been raised in all presentations, actually. We will get a different perspective on maritime electrification, that of a port. So I welcome Victor Alguren. Hope you are ready to speak. Victor is head of innovation at the Port of Gothenburg and also a former colleague of mine when I worked there 15 years ago. Welcome, Victor.
Thank you, Åsa. That means that I've been to the port at least 15 years.
Yeah.
Tragic. Is my camera working? I only see
No.
a black. Oh, strange. Anyway, we'll do without it. Okay, so what about the grid, the power grid? I will try to describe the port's perspective on this issue. If you move on. Okay, so as a port and especially a port authority, we work with infrastructure. That's what we do. We manage the fairways, the railroads and the roads and the terminal infrastructure. So this is our main objective as a port and a port authority. And the railroads, they have been electrified for 100 years. And the other infrastructure, that's sort of main issue for us. And if you press again. But now also the power grid is an essential infrastructure for a port as well. And it's not an issue. It's not now an issue, but it will be quite soon. So that's why it's been raised as a more important infrastructure for the port. And moving on again. And what's the characteristics of infrastructure? It's very expensive to build. It takes very long time. It has a long planning phase as well. And when you need it, you're already too late. You should have started 10, 15 years ago before you have the need. And planning ports is normally a 30-year perspective. And we don't have any sort of lack of power in the port or any port because all the transport uses liquid fuel. So the power that's needed is not from electricity, but this will definitely change for all the transport modes. And I think we can take the next one as well. So what is happening, or rather what will happen in any port, and especially our port, the Port of Gothenburg? Well, we have the shoreside electricity, which we've had for many years, but that will increase for more segments and more vessels as well. For sure, we will have electrical handling equipment in the port. In the Port of Gothenburg, we have plus 100 heavy machines taking care of the cargo. Those vehicles will definitely change propulsion to fuel cell or battery electric in the future. We need to charge the trucks arriving to the port somewhere close to the port as well. And as we heard today, we will have more battery electric vessels that needs to be charged. And that was stressed early on as what if we have more megawatt hours on the vessel? Well, we can't charge it in the port anyway, so it doesn't make sense. So that's a bottleneck. We will also see and we will have localized hydrogen production electrolyzers in the port as well, especially in the Port of Gothenburg. And another issue for the grid is not just what we need as a port, but what does our neighbors need close to the port? We share the same grid, and the Port of Gothenburg has important neighbors as the refineries and other production facilities like the Volvo construction facilities, and they will electrolyze even more. So it's not just up to us, what are our neighbors doing as well. This will happen. It has not happened, but it for sure will happen. And if we take the next one as well. So what should we do as ports? And what do we do? Well, first we have to check the available power in the power grid. What's the status in our location, in our port? And after you do that, or at the same time, you need to make friends with the grid owner. They have to be your best buddies as a port. And once you've done that, you need to simulate where are we at right now and where are we going, and what's the journey forward, what's the electricity and the power need for the future. And also while doing that, sort of realize and recognize that the power consumption in the port will be intermittent. So either it's on or it's off. Either a vessel is charging, either a vessel is connected to the grid, or trucks are charging or they are not. So it's not like a production facility with steady use of electricity. So therefore, energy storage makes sense, especially in a port facility where we have different vehicles in the port or they're not. So if we take the next one as well. So what's the situation in the Port of Gothenburg specifically? So we try to look at what's the power consumption, and this is also how do you calculate the power, not just the electricity, but the power. So the circles are the highest power situations in the Port of Gothenburg during 1 hour, and the lines are the power from the grid that's available right now. So there's a bit of slack. There's on some places we have available power in some places, especially the energy port right now. It's a bit tight, but this is the first sort of the status how it looks right now. And then you need to understand what the grid company can provide and what lead times they have and what bottlenecks they have. And it turns out that especially the Port of Gothenburg, which is located in a historical industrial area with refineries since 50, 60 years ago and production facilities as well. The grid to this location is quite strong. So there are perhaps an overcapacity of available 60 megawatt in our port, which is quite easy accessible within 1 or 2 years. So that's the knowledge that you need to understand as a port. What's the available capacity in the grid, and what lead time does that have? And if we move to the next one as well. So this is our power walk. This is how we foresee that the electricity and the power will be more used in the Port of Gothenburg. So we start up with 24 megawatts. That's the highest power that we require from the grid this year. And all the changes to this line are things that we foresee. As I mentioned previously, it can be shoreside electricity, it can be charging of heavy trucks, it could be the Stena Electra, which is the sharp increase in this line from 2029 to 2030, as we foresee it, and other situations as well. And if we press once again to the next one. So what we do is we monitor this each year. So the orange line is what did we foresee 2 years ago, and the green one is last year. So are things progressing more aggressively, or are they being put more into the future? So we will keep doing this in the future as well. And I think this autumn, when we'll do this again, I think we will have a line which is a bit higher up and a bit more early as well. So things are moving along slightly quicker. But our challenge, as you can see here, is that we need to reach 100 megawatts instead of 20 megawatts. So that's the challenge for the grid, to provide the port and all the activities with more than 300% more power than today. Yeah, and the next one. So I have a summary, and then I have a final one after that one as well. I think this is really inspiring, the transformation of the transport system. It has had one type of propulsion system until now, and we're moving into a new type of propulsion system, which is renewable and CO2 neutral, which is really inspiring. And we have not considered the power grid as critical infrastructure. As I mentioned, it has been the railroads, the roads, the fairways, and the terminal infrastructure. But now the power grid is equally important moving forward as well. And we need to plan ahead. So we don't have a situation right now, but we most likely will have a situation in the future. Therefore, we have to plan now for the situation we will have in the future as well. But also recognize that if we face lack of power, then we have really managed to transform the system. We've managed to reduce the CO2 emissions, and we've been able to introduce these battery electric and fuel cell systems in the transport system. So if it is a problem, then we have sort of managed to do good things. So I want to have a positive view on this as well. And I think the final one as well. So yesterday we had a press conference regarding a production facility of the first fast charging system for heavy trucks in Scandinavia. It will be built just outside the port of Gothenburg. So this it's Circle K who will enable fast charging of trucks, and we have more than 1 million truck movements to the port each year, and we foresee that this will be battery electric or fuel cell electric to a high degree in the future. And they need to charge. Mainly they will charge at their home depot, but they need to be able to charge as well sometime during their work day. And it's a chicken and an egg situation. First we build the infrastructure, and then the trucks will be able to deploy. So we're working together with Volvo and Scania and Stena Line in this Transzero initiative. And it's also an observation that it is able to work with companies that are sort of competing on the market, but still sort of collaborating together to make these changes, as Volvo and Scania is one example. In other cases, we have Stena Line and DFD is joining forces as well. Okay, I think I'll end there.
And say that the port is 401 years old.
Yes.
Thank you very much, Victor. As I understand it, the port of Gothenburg is one of the lucky ones with a lot of overcapacity. Do you know how situations are for other ports, nationally or globally?
Yeah, I mean,
do you have a better spot than them, or what do you think?
Yeah, and exactly. So sort of this, you have to start and realize, are you a lucky one or are you not? We happen to be that. We didn't know that before. And I think most ports are not as lucky as we are to have that overcapacity. I think most ports are located sort of at a good location, and that doesn't necessarily mean that you have a strong grid. So you have to check your status. And I think most ports do not have the same sort of possibilities that we have. And for them, I think these types of energy systems, energy storage systems in different shapes will be even more important. So I think that we are in a very fortunate situation. I don't know any other port that has done this sort of checking their status on the grid, but I recommend them to do that.
You have a question here from Sven Borén. If you have looked at having energy storages instead of using only the power grid?
I think we need both sort of reinforcing the grid. And I know that Pelle will talk about that later on. We are involved with that project. And I think that's one of the important components for sure.
And speaking of, Per Wingby, he has a question to you.
Thank you, Åsa. Thank you, Victor. I was just thinking, we've been heard now that the rope access and the RoRos are connected, but then also heard about in the energy port that you will also connect the tankers. Could you tell us a little bit about that project?
Yes, that's extremely sort of happy to do that, because that have battery electric systems on tankers is truly unique. So that will not draw that much power from the grid initially. That would only be one megawatt. So we will manage that. And that's also for the small product tankers. If we move up in size with this type of system, then it will sort of require more from the grid. And it's also working together with especially the Dons shipping companies that call the port quite frequently. I think the benefit for RoPax and ferries are that they are sort of one or two ports that they stay for many years, but the container and the car carriers and the tankers, they go to many different ports. They don't know which ports they will call for their lifetime. But the Dons tanker companies, they know that they will call the port of Gothenburg for many years to come. So they wanted to do this investment, and then we're connected that. And that has some challenges, of course, with the ATEX system. We cannot have anything explosive in the energy port. You're not allowed to have your cell phone on in the energy port, so you have to have sort of overpressure systems both sort of on the grid and on the vessels as well. So it has some additional technical challenges, which makes it slightly more expensive as well. So it's an industry first. So I think and hope that we will be closely monitored by the rest of the world to introduce this.
So you are actually the first port in the world to connect the tanker.
Yeah, I'm quite sure that we are. I haven't heard anyone even look at it. So I think it's we should be. I think as the Swedes here, we should be proud that we are sort of moving into electrification of tankers and sort of set to aside that they are transporting fossil fuels. That's what they do. They still should do the best they can do, which is it's a good.
Like a little more than 15 years ago, there was a study tour with a lot of people from Gothenburg visiting Los Angeles, and they were talking about that they were going to make it mandatory for tankers.
Yeah,
but they haven't achieved that yet.
I don't think they have, but I will have to look into that.
I don't think either. So
no.
Thank you very much, Victor. And I have one other question. Do you actually plan now to produce your own electricity, not just storing and receiving from the grid? I mean, will have electrolyzers, you say. Will you also be very positive and put up your own windmills, or what?
I think we will look into that, but we should be ashamed as the Port of Gothenburg to have that low energy production. But it's not the electricity that's the problem, it's the power that is the challenge. So even if we produce power, electricity with wind or solar, is it available when we need it? That's the main issue. If we need to charge the Stena Electra and the wind is not blowing, then it has any value. So the grid and storage is much more important than energy production. But yeah.
Okay, thank you very much, Victor, and I hope you will stay for the rest, so if there are any further questions.
For sure.
And then I will leave the floor to Per Wimby, who is from Stena and project manager, has devoted more than 25 years of your life to this company, actually. And now you will talk about a project about energy storage. So please, Pelle.
Thank you, Åsa. It's actually 26 years now within Stena. But as the previous speaker have said, charging is a big bottleneck for building battery ships. I mean, Bengt just said that we have the technology to build the ships, but the charging is a problem. And it's actually two challenges. One, if the power is not available at the key. We heard from Victor that in Gothenburg is not a really big problem. And the second is that if the power is available, the cost for the grid is very high. For example, I mean, we're not a good customer, or we are a good customer for the grid owner, because we need the power very high power in such a short time. And the system it works today, with the business model that they have, is that they charge for the maximum power you use. So, for example, if we have one ship, only one ship, electric ship from Gothenburg to Frederikshavn, we will end up with a cost of roughly 10 euros per kilowatt hour just for the grid. So in the Sea Lion project, we have the idea to use second-hand batteries, mostly from the automotive industry, to build up an energy storage system on the quayside, and that will decrease or reduce the power need from the grid. So that's the whole idea. Yeah, and again, my name is Per Wimbe, as also said, from Stena Teknik, and we will hope that this Sea Lion project will boast sort of the use of electricity in the marine sector. As you can see, this project is financed, co-financed by EU from CEF, Connecting Europe facility, and we also have a name called Battery Loop, which is a newly started company within Stena Recycling. They are both on mobile units, connecting ships, etc., but they're also on existing fixed units like housing, etc. So if you take the next chart, I will start with telling the story, the timeline for Stena Electra, which is the common name that we use for our electromobility within Stena. And it started a long time ago, 1989, where we connected the two German ships trading from Gothenburg to Kiel. And that was using low power, low voltage systems, a lot of cables. And we changed that in 2005 into high voltage system, 10 kilovolt systems with just one cable, as you can see in the picture in the left. Then we had another interesting project, also connecting ships using the central heating in Gothenburg to actually heat the ships. That was connected, but not with electricity. And then in 2014, we introduced or started a project with the all electric ferries for Helsingborg-Helsingör route, which was at that time a part of Stena. Now it's not. So we did not finalize the project, but we set up the scope, and we also managed to finance the project. 2018, we started with what we call step 1 on Stena Utlandica, which is an energy storage on board the ship, which is sized 1 megawatt hour of batteries, with the main purpose of feeding the big consumers on board, such as the bow thruster and other equipment on board. And that's the sort of the main purpose, but it also is a big UPS for the whole ship. Actually making the ship sort of what we call a blackout preventer, and it's actually helped us several times. The third sort of also fantastic thing is that it minimizes the use of the auxiliary engines. So it's a peak shaver, that's what we call it. And it's actually, we only use one auxiliary on board and set it on a fixed power, and then the battery will take the load peaks. So yes, this year or last year, we started with this ESS Sea Lion project, and it will go on for 2 years. We think in a couple of years, we will have the step 2, the hybrid solution. That means that we will run on battery electric through the archipelago. And then when we come out in the open sea, we will run on our diesel engines. And the third step with a full battery electric ship will be in 2030, roughly, with the Stena Electra, or the Electric Light. So I will just briefly tell you a little bit about the project, Stena Sea Lion. I don't have any conclusions yet because we are sort of halfway through the project, but we had some good partners here. We had the Port of Kiel, and we have Victor in the port of Gothenburg. We have DNV mainly doing the safety part of it. And we have Stena Recycling, which is called Battery Loop, who is doing actually most of the work in this project. And we are sort of the coordinator of the project. And again, yeah, we have the grant agreement there. Yeah. So first of all, we have 5 different work packages. The first one is actually to design the system, looking on the requirements. We have sort of done that. We are halfway through this or even more. And one big thing is, of course, to look at the needs, exactly what Victor showed us. What is the need of energy? You can go to the next slide. And then the second part is actually using of these recycled batteries. If we take the automotive industry, they are quite, the capacity, the requirement on the batteries are much higher in the automotive industry. For example, the sea level is much higher than we need, and also sort of if a user of an electric vehicle finds out that he has not the capacity left in the range in the car, he will complain. So they have to replace the batteries, but we can use them for battery storage. And of course, the cost is much lower for a used second-hand battery. Yes, Åsa. And then we look on the grid impact, and we looked in different ports to sort of make an inventory of what is the shore power is available, and also looking on the grid. And we make sort of a cost-benefit analysis comparing using the grid directly compared with using energy storage on the quayside. Next slide, please. And then, and here's our part of it, to see if we can make a business case. The business case is always important to show. So this is what we're heading for. And hopefully, work package 5, in 1 year's time, we will have a dissemination of the project. So then we can tell you more about the findings of the project. So thank you very much. That's what I've had.
Thank you very much, Helle. And when you have finalized this project next year, of course, we want to participate in disseminating all your results. But do you think this project will result in an actual installation of energy storage at shore?
I think it will. That's our findings so far, and that's also the findings that we have in our internal projects in Electra, that we cannot pay this 10 euro cents for the grid. We must come down in cost, and using energy storage will reduce the cost. I think to make a business case, the grid cost cannot be higher than 2 or 3 euro cents, because then you have to add the energy cost itself, which in Sweden is sort of 5 euro cents. And to make the electricity on board using diesel as it is today, the cost is sort of 10 euro cents.
So when do you think this will happen?
I think the need will come when we have high power ship like the Stena Electra. So in 27 or something.
Even if
also we see an increasingly need, exactly what Victor said, for our customers to charge their vehicles. So that will probably speed up the process, I would say.
And then I would say now to something completely different, because you're also working with a project exactly about that, aren't you? About charging cars on the ship. How is that going?
We have one of the board members of Stena is Lottie. What's her name? Well, she's from the travel industry anyhow, and she said you have to fix this. The customer is requiring that you have to charge your cars. You have to come to the port to do destination with a fully charged car, and we have to fix it. And so we're trying it out now on Stena Skandinavica. So when you arrive in Kiel, the car is fully charged. But we had some hurdles there are two things actually. There's the safety, but also the economics in this to make it work. And so yes, it's ongoing. Yeah, also.
Good. It'll be interesting to see where you land. And are the customers are they prepared to pay for the service?
I think we have a good opportunity there. I think we can provide them with sort of a okay price, because the pricing on shore is quite high. You see a charging station where you have to pay like up to 4 or 5 kronor, as a 50 euro cent per kilowatt hour, and I think we can come down in cost.
Okay, thank you. Are there any questions to Pelle from the audience? Since you have posed so many questions, so somebody will have to take your role, don't you think? Peter Peterberg from Färjerederiet, please.
Yes, I just had some questions about battery safety when using a used battery ashore. Are you going to look into that as well?
Yes, that's part of the project, and we will probably end up that we will use the cells and we will make our own battery management system to facilitate the safety. Yes.
Okay, interesting project.
Yeah, the requirements, as we understand it so far, is much less on the key side compared to on board the ship.
Okay, thank you.
Sven Borén from Blekinge, please.
Yeah, I was just wondering if you have considered other technologies than batteries, used batteries, or is that the way forward for you? The only way forward for you, sorry.
I'm not sure if it's the only way forward, but that is what we are looking at. And we hope that there is a big industry for used batteries. The installation that Battery Loop has done so far in residential buildings are actually new batteries. But we're hoping to see that there will be a big market for second-hand batteries. But it's only batteries until now, yeah.
Maybe 2 or 3 years ago, we had a seminar about maritime electrification, and then there was this Bo Normark, who's been working with electricity and batteries all his life from ABB. He said that you should use the used ones. That was his takeaway at that time, when there were almost no maritime use of batteries. Harry Robertson from Stena would also like to pose a question.
Well, yeah, just like to highlight that there isn't only technical issues that needs to be solved to have an energy storage that is useful for the rest of the grid and so on. I think there is some regulatory issues to be solved to be able to take full advantage of the energy storage. Isn't that the case, Pelle?
Yes, I would say so, very much, yeah.
And you will solve these also in your project, or at least look at them?
Yes, we will.
Okay, thank you very much. And I have now, you see the slide here, I show the program, and we have come to discussion development of maritime electrification. And you can actually pose a question to any of the speakers, or and I also have a co-host here, Mikael Hägg, if you have any questions, please. So then I will start.
I can just say a couple of words. The idea with this webinar was to start to present with the results from Lätta elfartyg and Electric Light, and then we have looked into a bit more in detail in those aspects that we think is critical. It was the batteries, it was the battery safety, it was the port perspective, and we have also seen upcoming projects. And there will also be hopefully follow-on projects to Lätta elfartyg. One more in the line with lightweight and high tension steel, how to use that, and another project where we will go further into this draft safety concept. So that was sort of the purpose with this webinar, to highlight some of the critical issues here. Yeah, Åsa.
Mm-hmm. And if you are interested in any of these projects, you can contact us or Mikael or Ola Willstrand at RISE, because they are writing the detailed descriptions of the projects now, and it is possible for anybody who is interested to attend. But speaking of projects, I know that Charlotte Andersson is participating, and she's from Trafikverket, and we are very happy that actually you have, with your industry program, funded this project, Electric Light. Would you like to say something about if you think it's worth the money, maybe?
Let's see if I can even get my camera on. I don't know if I'm in. Yeah. We started this program about 2 years ago, and it was the first time that Trafikverket had this type of program. So it was a bit of a new way to use the finances that are available for us. So I think that we can all agree that we are now 2 years into the program, and we have started and received a lot of interesting projects, and now we're starting to see the results. Today, it is obviously that there are still a lot of challenges. We are not done. We need to continue to finance these projects. So I'm just very happy that we have this forum, this platform to have these type of projects. So thank you for a very good job done.
Thank you, Charlotte. And thank you for allowing us to run this program. Victor, please.
Yeah, yeah, I have. I think when sort of moving into the electrical system for transport, you cannot just do the same as previously and sort of operate the same as previously. And as an example, when Pelle mentioned the Helsingborg route, where you have the electric vessel, they need 10 megawatts to charge during 9 minutes. And they only have a 4.5 megawatt hour battery. So they drain the grid both in Denmark and Helsingborg quite extensively for that small ship. But they want to have the route just as previously. If they had 18 minutes of port stay, they would just require 5 megawatts instead, which is a huge difference. And also for the Stena Electra, if they want to turn around the ship in 1 hour and they require 30 megawatt hours, then you can understand that they need plus 30 megawatts from the grid. But if they can turn around the ship in 2 hours instead, they just need 15 megawatt. So you need to take the grid and the peak grid charging and the costs and the complexity there into consideration. Perhaps you need to have a longer port stay in Denmark and a shorter port stay in Gothenburg when you consider the grid and the cost for the grid and so on. So it's completely different. You can't just introduce electric trucks and electric vessels and do the same as you did previously. You have to consider both the cost and the availability and the peak charge and so on, which is another dimension. Yeah, just wanted to say that.
Thank you. I have a question from Sven Borén. I wonder how much more energy will be used if the electric ship to Fredrikshavn had 14 meters per second headwind.
That for me, 40 meters per second.
14.
Yeah, of course. We have some sea margin into our analysis, of course, but we will probably be late. But there is a built-in redundancy that batteries, we talked about depth of discharge, and so there is a margin there that we can use in emergency. So normally we only go down to sort of 50% of the capacity of the batteries, but in an emergency we can go down to 10% remained in the battery. So that means that we have sort of double the power available.
You want to comment on that, Bengt?
Yeah, I think that's a very good question, and it touches a subject there that is important. With as I mentioned, the electric energy you have, or if you store the energy as electricity on board in batteries, it's very precious compared to diesel, where you can add a little bit more. So that means that we will not have. We have to make this feasible. We have to take away quite a lot of those margins we have had with a conventional ship. So it might be that situations we will have conditions where we have to accept to be late in order to maintain this really low energy consumption. So I think that will, of course, that the market will decide, but I think we will not be able to have the margins that we have been spoiled to have with diesel powered ships.
What range do you think what's the longest range you think is possible now, and what do you foresee? Anyone can answer that. I mean, it's allowed for anyone to answer because it might be a tricky question.
I can say something. I think there's 50 nautical miles. It's good. We at Chalmers, we did a design project this fall where we were looking for called Kuna Gdynia. That is too far. It didn't make sense to have a battery powered ship. But on the other hand, there was very good conditions for sailing, that we could have a sail assisted ship. But those overnight 100 nautical miles, I think that really gets into the far end of what we can achieve. And again, I think the bottleneck will be the charging again.
Mm. Could I pose a question? Oh, okay.
Question here, because Chris, I mean, how far from Nynäshamn to Visby? How far is that distance?
Christer has had to leave, so he's not here any longer.
Well, I think 100 miles would probably be okay. We have the capacity of the weight, and I think volume-wise, a ship is perfect for the use of batteries. The problem that they have is the speed. They have to go down in speed, I would say.
Okay.
Marcus Högblom here from ABB. Maybe I could comment also. We have done quite a few of those ships. So I think this just some comments on this grid and these other things that I think what we see when we work with these different projects of world is that you really need to kind of get everybody on board, also the grid and the port. And sometimes there's a little bit of a, how should I say, bureaucracy there and maybe not the political will to do this. But as for the length, I think this 100 nautical mile can be achievable if they have a ferry that doesn't go, like, has a sufficient of charging time and speed is not too high. So we could see, for example, also Vasa Umeå could probably be done on that one or something like that. So there's quite many possibilities to do it. And then of course you could have a hybrid solution also with fuel cells.
Is anybody from, I think somebody from Färjerederiet, would you care to say something about your experiences with?
Yes, I could say something. Fredrik Almlöv. I think we're in the process of electrifying Gullmarsleden now, and it's very interesting to hear everything that has been said and so on. And our solution is take me home generators on board, but maybe that's not possible for the Stena project because it's need to so much so large engines anyway. If you should have a take me home generator or something.
Okay, thank you. And I think Victor also has a comment. Victor Algren, please.
Yeah, talking about Lätta elfartyg, we have a small vessel, inspection vessel in the port of Gothenburg just for 24 seating, going around the port, MS Hamnen, which we hopefully will electrify. And they normally do 3-hour runs in the port, but they need to be able to operate 24/7. So if we would have a full electric vessel, we would have a lot of redundancy never being used. So we will have sort of batteries enough for 3 hours, and then we will have a diesel genset for those rare occasions when they need to be on the sea for much longer time. So instead of sort of having that capacity in batteries, we will have it in diesel to cut down the cost. So it depends on your profile, but when our vessel, sort of 80% of the journeys are less than 3 hours, that's what we build batteries for, and then we will have diesel for all other journeys.
Okay, thank you. Are there any more comments or questions?
Yes, Åsa, if I may.
Yes.
I mean, like I said in my presentation, that the cost for the grid is very high. And I wonder if you could do sort of a sharing of the grid, that we consumers go together and share the grid if we have different needs. I don't know, Victor, what do you think about that? Because you will have a lot of charging of vehicles during lunchtime. And maybe we don't need that. If we can sort of set up a different business system for that.
Could I add something before Victor answers? We actually, in the port, we had the grid in Frihamnen. It was our grid, but I'm not sure if we were allowed to actually keep it because we were selling to customers, and there's, you know, it's called koncession. So I think we had to sell it back to the net company. But you, Victor, please.
Yeah, so the grid company, they have the monopoly, but it's possible to, with this flexibility market, to sell electricity. They will open up that. But especially for batteries, you can move them around to put them on the truck charging location, which will require power during lunchtime, and different vessels as well. So I think for sure, if you have a battery system, that's a business opportunity, both to solve your own problems, but then to generate electricity for others as well, and to make the grid stable and earn money for that. And I think there are different technical solutions for sort of if you want to have your own electrical grid in your terminal to provide electricity for some services. But especially if you have a battery, you can sell that electricity back to the grid when the price is high, or you can move it around to other consumers in the port, which is really interesting. Especially if vessels are on schedule and trucks are charging at lunchtime every time.
What you talked about now, I was thinking about, there's been a lot of discussions about smart grids, but do you think there could actually be a market where you could sell and buy power?
For sure. And I also think that as a port, I think that we can be for the vessels that are using onshore power, that is not just pure electric. They can connect to the grid, or they can use the diesel engines. They can sort of make a promise to the grid that if the grid is sort of constrained, they will not use the onshore power, and they will get paid for that option. Just that there are some high electricity consumers in Sweden that will disconnect if the Svenska kraftnät require them to do, and they will get paid all the year for that option. So I think there are many sort of new business models that will develop, and especially around the port, which has this intermittent energy, and for sure for vessels that have the possibility to use the diesel engine, and to promise that they will not use the grid if it's really constrained, for instance. But for sure, moving around energy storage systems in the port is a good idea, and to sell that energy solution.
Yeah. Okay. I see we are now at 11:04. I was looking at another watch and it had stopped at 10:59. So I thought very long minute. Are there any other questions or comments you want to pose, or should we?
I can just say thank you to Mikael and Bengt for a fantastic project. Sort of purpose-built for Stena, but I hope more people can enjoy the report. Very good, very well done, I would say.
Okay, and I would like to say thank you very much to all participants and to all speakers and to Trafikverket, of course. And I hope you've had an interesting morning and that you will have a lovely summer vacation. And to ensure that it actually is a lovely summer vacation with a lot of interesting things to read, we will send you all the final report of the Electric Light Lätta elfartyg project in PDF format. So thank you very much, all of you, and hope to see you in real life this autumn.
Okay. Bye-bye.
Bye.
Thank you.
Thank you.
Thank you.
Thank you.